Okay, so I think we should get started. Welcome, everybody. We are restarting this weekly series of seminar hosted by the Simon's Bootstrap collaboration. So we will try to have a seminar every Wednesday. We will announce the seminars on the Slack channel of the collaboration. By the way, if you're not on the Slack channel, you'd like to be, please send any of the PIs of the collaboration an email, and we will add you. And or go to our webpage and ask for an invitation there. And the seminar schedule is also posted on the research seminar general schedule of Zoom seminars. We do not have a seminar schedule yet for next week, but yes, for the several following weeks, we will try to schedule something next week. So please stay tuned and find out on either on the Slack channel or on research seminar whether we're going to have a seminar. So today we are glad to restart the series with Junchen Rong from DESY, who will tell us about the old conformal bootstrap revisited. Thank you.
Okay, thank you for the invitation. Actually, it's a great opportunity to present our work. Yeah, please interrupt me at any moment as usual. So this work, the title is called The Old Bootstrap, which actually has another name, which is called the Migdal and Polyakov Bootstrap, as developed by the founding fathers of string theory, actually. So this is work is based on a preprint appeared a few weeks ago, and is in collaboration with Pedro Lindo, who is also a bootstrapper, and also Junchen Liu, who is actually an amplitudologist. I hope I pronounced that name correctly. So it's called old bootstrap. This is because it's the approach that people were taking before the modern bootstrap was invented, and which is based on, we all know, is based on 4-point functions. And this old bootstrap approach was actually based on 3-point functions. So to start, let's start a little bit with history. In fact, in the 1982 lectures of K. Wilson, he said, if the 1971 renormalization group idea has not been invented, the Migdal and Polyakov bootstrap approach would have been the most amazing framework of its time for trying to understand critical phenomena. So let's go back in time. At that moment, I think conformal symmetry was not quite clear at that point, and the renormalization idea was not clear. So the approach is based on a series of works by Migdal and Polyakov. Basically, mostly importantly, it's 3 papers. So this approach, in these papers, they realized 2 important things, essentially. So the first thing is that they realized by analytically continuing the Euclidean field theory, which is statistical physics system, back to Lorentz signatures, one can use the unitarity conditions of Euro quantum field theory to derive bootstrap equations for propagators. So yeah, the original bootstrap equation kind of looks like this, as I said. So it's based on an earlier work by Gribov and Migdal, which was working on quantum field theory at that moment. And the connection between Euclidean and Lorentz signature was probably clear, or was probably clear for has a longer history. But what was realized in this paper was that you can indeed use in these conditions to derive important self-consistent conditions for your correlators, essentially. So what appears here, the diagrams, these lines are propagators, but really they mean the fully dressed propagators, the actual propagators. Actually, I think here is retarded Green's functions. And the imaginary part of the retarded Green's functions gives you the spectral density. And this is kind of looks like the optical theorems. So this diagram basically gives you the self-energy of your calculation of renormalization. And you remember the self-energy actually appears in the denominator of your propagators. So that's kind of why there's negative, there's an inverse here. So okay, the formula essentially looks like this. You still have the piece that has the gamma 4, which is the 1 pi effective vertex for the 4-point functions. And because of this, there's no clear way, really no clear way to derive this, to solve this equations. In fact, because there are two different functions. But what Polyakov did in his paper was actually he tried to solve the, he put an ansatz for these propagators, or the inverse propagators, and you take the imaginary part at the Lorentz signature, you plug it back in, and you can derive the relations between the scalings for this gamma 4 and the scalings of this D's. Basically, that's what he did. So he actually did a little bit more. He was trying to basically move away from the critical points by introducing a small scale.
Sorry, where does these ansatz come from?
This ansatz basically is, well, it's because of scaling symmetry, essentially. So we are dealing with a critical point. So the propagators would just be the scaling.
Okay.
Yeah. So yeah, so I think this type of relations was actually done in slightly earlier work by Patashinsky and Prokhorsky in 1964. So in that paper, they were trying to deal with this contact gamma 4 terms as contact terms, basically. They just ignored this gamma 4 and treat this gamma 4 as a contact term. And therefore, you can see that on the right-hand side, if you ignore this gamma 4 and ignore the higher order terms, you can actually find kind of self-consistent relations for this power alpha. Just from the dimensional analysis, you can actually solve what this alpha is. It's kind of guesswork. So first of all, treating gamma 4 as contact interaction are not really correct. And also another thing is that that calculation was based on, was done in Euclidean space. And this connection between Euclidean and Lorentz signature was not clear in that paper. So it's kind of that the calculation was not in really solid ground, down in a solid ground. So yes, this is what was done in the first two papers. This one, actually another piece of information was included. It's basically the importance of conformal symmetry. So conformal symmetry basically help us fix the fully dressed propagators. Right? This is a fully renormalized propagators after you do consider all the loops or whatever in the actual safety point. You have these power law behaviors. But on the other hand, there's another thing that's important is that it helps you fix the so-called 1 pi effective vertex. So I'm denoting the shadow field of phi as phi tilde in this expression. But the 3-point function of the shadow field are basically the 1 pi effective vertex. This is because you can do this calculation by attaching the one particle states, one particle external legs onto this 1 pi vertex. You perform this integration using semantic star triangle formula. And in the end, you get that your 3-point correlators actually looks like the usual correlators we are more familiar with, and with some constants in front. So indeed, this Tudor field, this shadow field, 3-point function are the actual 1 pi effective vertex, as the ansatz for the 1 pi effective vertex. Okay, so so with these unitarity conditions and also with this conformal symmetry, you can actually write self-consistent conditions for the system. So there were two equations was considered. One is for the vertex. The left-hand side is the 1 pi vertex. I'm using orange dot to denote the 1 pi vertex. Is basically its form. But after renormalization, you consider all the loops of renormalizations, it should come back to itself, essentially. So these are 1 pi vertex, so they are coordinates here. So yeah, okay. So you have one for this one Pi vertex. So notice one thing is that there's no Baire term here. I mean, in Euro renormalization, we should add some Baire couplings to cancel the infinities. But in here, there's no Baire term. So this was suggested by Migdal in his paper. And I think this is actually, it's very clear, it's due to universality, right? So you shouldn't really care about the Baire coupling, which is basically coming from the wave physics. And also another thing is that this expansion is the skeleton expansion. Means that these are really the four 1-pi vertex. Diagrams like this should not be included. Yeah, so instead of using this form proposed by Polyakov and Migdal, we are going to use another form proposed by Mark and Nazi, which is a little bit more convenient for us.
Actually, can I ask a question, Junchen?
Sure.
This equation at the top of this slide about the vertex being equal to the sum. Is there some way to derive this equation, you know, by, for example, I don't know, by starting from some theory which also contains the Baire term and then somehow going to the infrared and seeing that this equation arises in some kind of in the infrared limit? Is there some way to derive this equation? It looks suggestive, but you didn't derive it. And so I was wondering,
yeah,
did you derive it or did you just postulate it?
I think probably the direct way is just to start from path integrals and actually consider the renormalization counting all the diagrams on the right-hand side. And then you group themselves together as skeleton expansions. I think you probably would arrive at this kind of diagrams.
But what
Basically,
I'm worried about is that if you try to do it in field theory, then, for example, the exact vertex in field theory, it will contain some UV part and it will contain some IR part, and you kind of assuming that only the IR part, which is described by the CFT, which will dominate all integrals, while the UV part will completely drop out. So that's kind of needs to be checked whether indeed every diagram is going to be completely dominated by IR.
Yes, I think if you talk about that kind of proof, I think there's no this kind of proof. It's yeah. So I think I'm going to mention later because these diagrams they are finite. I will show later. They are finite, so you don't really need the Baire term to cancel the infinities. They are finite because we are at not at the free theory value of the scaling dimensions. We are at the critical dimensions essentially.
And sorry, a naive question, because I'm still a bit unclear about the conceptual underpinning all of this. In this kind of expansion, you only have an elementary cubic vertex, no quartic vertex, or this is just
yes, I mean, okay, I should mention that we are considering lambda phi cube theory at this moment. If you want to do Eisen or Owen vector models, you can introduce the kind of vertex with like 2 sigmas and 1 sigma square, which you treat it as a single field, and you can write equations, similar equations for those vertices.
I see. So I should think of this cubic vertex as really arising from some sort of Lagrangian coupling. It's not the abstract 3-point function of the CFT.
Yes. And actually, I'm not. I don't know. I'm not sure if for example, for a random quantum field theory, you forget about Lagrangian. Can you still do this? Have this kind of relations? It's not too clear to me. But I think for the moment we should probably restrict ourselves to the Lagrangian description.
At each order in this expansion, for a given number of vertices, is there a unique graph?
Yes, there is a unique graph. I think, yeah. So it's not too much different from the Euro Feynman diagram countings. I think so. I was basically suggesting this. So you first do a Feynman expansion, and then you look at what kind of subdiagrams would become the renormalization of the vertices. So therefore, you group them together, and you arrive at skeleton expansions.
In this expansion, there are graphs
Yeah.
which have a new topology, which in conventional perturbation theory tend to generate things like zeta-3, zeta-5, and so on. But I think once you go to about 4 loops, there's more than one topologically distinct graph, which I think you can add in.
But these graphs also, I mean, they also comes from the usual Feynman diagram expansions, right?
Yeah, but you're summing up various things. But I mean, at any given order, there are graphs with a new topology.
Right. Yeah, I think similarly here, if the graph with new topology appears in the Feynman expansion, there should be similar things appear here. Is that clear, or should I continue?
That's fine.
Okay, thank you. Yeah, so these are the 2 equations, and let's look at it in a little bit more details. What the Bootstrap equations looks like. So let's focus on the leading diagram for the moment. So the leading diagram looks like.
I'm sorry, Junchen, I'm kind of I'm lost. So you mentioned also this max semantic equation. So what's the difference between the 2 formalisms?
Okay. I sorry, I forgot to mention that this is in fact in this paper they showed actually it's quite complicated, but they showed that they are equivalent, 1-to-1 correspondence.
Okay.
To the Polyakov's representation.
Okay.
Yeah. So let's look at this diagram first. So this leading diagram looks like this kind of integrals with the integration at the point x4, 5. Notice these are really 1 Pi vertex, so this coordinates needs to be integrated out.
So you said it, but I forgot. Phi tilde is the shadow. Is the shadow field?
Yeah, it's a shadow field. So I'm using it as a shorthand notation to denote the 1 particle irreducible vertices, essentially. So yeah, so from here, the shadow means the 1 particle irreducible vertices. You attach the fully dressed propagators. After doing star triangular formula, it goes back to the usual 3-point functions. Yeah. So we are doing this kind of integrals here, so I should say under transformation, under conformal transformation. In fact, the measure, the D measure, transforms in this way, and with a power which is -d. The field itself transforms in this form with a delta, with a power which is delta. And on the other hand, the shadow field transforms with d minus delta. So altogether, this combination, they are invariant under conformal transformation. So this means that the integration at x5, let's see, x4, or all the middle coordinates, intermediate coordinates, they are invariant under conformal transformation. So this whole integral would transform as a 3-point structure, which is conformally covariant, which should look like exactly the same kind of structure as the left-hand side. So suppose you are able to perform this integral. In the end, what you are getting should be a number times the 3-point structure of this phi tilde 1, phi tilde 2, phi tilde 3. So you can factor out this 3-point structure from left-hand side and right-hand side. So you will get this equation that looks like this, essentially. So I'm performing this integral, and I'm factoring out the 3-point structures, and in the end you should get an equation like this. This is indeed an algebraic equation. There's no coordinate dependence. Okay. Similarly for the stress tensor, and you can see that again for the intermediate coordinates. Phi and phi tilde comes together. So in the end, this whole diagram should look like the stress tensor between T and phi. So again, you should get an equation like this. So we have 2 equations, one coming from the renormation of the vortex, one coming from the relation of the stress tensor 3-point function. So, and we have two unknown variables, right? They are basically G squared and delta. So in principle,
I'm sorry, Junchen, but you said that they proved that their equation was equivalent to the other equation. So I'm confused why you're still considering Mach and semantic equation.
well, because
Didn't
it's
you
more
say it was
convenient.
equivalent?
No. What I'm saying is that this guy is equivalent to this guy. This guy is Polyakov's, is for the propagators.
I see.
But this vertex one is the new one.
Okay.
Yeah. So we are going to consider these two instead of this one and the Polyakov's.
Okay.
Yeah.
Thanks.
Okay, so now we have two relations. One is this, one is this. So the task is actually to perform these integrals. So I should mention some general properties of these Feynman diagrams. So these generalized Feynman diagrams are meromorphic functions of delta, essentially. So this was shown by Spear in his PhD thesis. They only have pole-like singularities. Okay, and also I should mention that the arguments about conformal covariance of the generalized Feynman diagrams works only if the integrals are free from the divergence. If for this integral you have some infinities, you have to think about how this infinity transforms and conform transformation. And the argument I gave about this phi and phi tilde and d appearing together are not so concrete anymore. But in the paper by Migdal, he conjectures that there exists a region that such integral converge. It was conjectured there, and it was proven by Mark and Todorov for Yukawa series. But for our case, for the phi cube case, in fact, this region is the region that the integral actually converge and without any infinity. So you can think about the poles as kind of like the free serial value, the usual perturbation limit. That's what's causing trouble and causing all those infinities. But if you are really calculating these integrals at a fixed delta, at a physical delta, these integrals would indeed be finite, and you don't really need to care about including cancellation of infinities.
I'm sorry. So even if you just pick some delta where the integrals do not converge, but you can define them by analytic continuation, you're saying then it's not obvious.
No. What I mean is that there's proper ways to do analytical continuation, and as long as you can do analytical continuation, you get rid of the infinities.
Okay.
You are fine. I think
Okay.
the composition phase is fine.
Okay, sounds good.
So in fact, the really hard work is to do analytical. Sorry.
I mean, the analytic continuation is often towards a pole, right? The physical value is often at a pole, and then you still have to be normalized, and then you can still get infinities. No?
Yes, you can still get infinities, but I think it will be clear after a few slides. Maybe let me.
Okay, sure.
Yeah. So so there are two modern techniques to do this kind of analytical continuation. So for this kind of Feynman integrals, we are lucky. One analytical continuation is based on Migdal representation, and another is so-called sector decomposition techniques. So so first to write a Migdal representation for these integrals. In fact, you can be complicated for usual Feynman integrals, but because we are dealing with conformal integrals, in fact, we can use the work by semantic actually to write Migdal representations very easily. So in fact, we need the generalized star triangle formula. This is indeed a star, right? You integrate out the x coordinate, and then you get rid of this. These are propagators connecting this x. And on the right-hand side, what you are getting is you get rid of this x. These are some powers, But the price to pay is that you have to integrate over some coordinates, some powers along the imaginary axis. And as you can see, so let's look at what n equal to 3 if you are looking at 3-point function. And this integration, you don't really need to do integration, and it goes back to the original star triangle formula. If you are doing 4 points, on the other hand, if you have 4 legs, you will have to do an integration with 2 integration variables, because you plug 4 here. As that we denote as S1 and S2. So that's this S matrix. Essentially, when you have 4 legs, you need to integrate S1 and S2 along imaginary axis, and you need to deal with these gamma functions, and these powers would contain this X. So I forgot to mention that these deltas, the summation needs to be equal to D, so that this middle point is conformally invariant. Okay, so this helps us a lot in terms of deriving the Migdal representations. So initially, the diagram, I'm enlarging, I'm zooming in the diagrams. This is the original 1 Pi vertex. I'm just denoting as a triangle now. And in fact, now you can use star triangular formula for 3 legs here, no, here, and here. You arrive at these diagrams. Now you would have to deal with 4 legs, and therefore you have to use the generalized star triangle formula. And you can remove this leg, get here, which gives you 2 integration variables. And now you remove this leg, you have another 2 integration variables. And this guy does not create any further integrations. So in the end, your formula, this expression looks like this. There's an I hat piece, which this piece comes from the initial 3 star triangular formulation, but you also have a Migdal representation in here with 4 integrations. So, what semantics, when semantic derive his formula, you actually require all these gammas in the numerator, including the ones in kappa, to have positive real parts as you chose your contour. So you can check that this is only possible if you are in this region. This is also the region that the integration is finite. The Feynman diagrams is in the finite, is a finite region. So this looks a little bit more complicated. Let's look at a very simple example, which is this simple integration with 2 gamma functions, one with Z, one with lambda plus Z. Sorry, it should be minus Z. Okay. This guy has poles along the axis, and this guy have poles basically along here. So your integration contour need to separate these 2 variables, essentially. These 2 series of poles. But this is only possible if there's no poles touching, right? For example, if the pole at Z equals minus lambda touches the pole at Z equals 0, there's no contour you can choose to separate these 2 set of poles, and your contour would need to touch the pole. That's what's causing you the singularities. So in fact, I mean, we can just do this, but because of we want later to numerically evaluate these integrals, this is not very convenient. So the convenient way is actually to just pick up the pole and have a straight line integration instead, right? So that's what we did. What you do here, you pick up a piece which contains the poles, but this guy would be a straight line integration, and also it can be evaluated numerically, and that's essentially the story about the analytical continuation. So I hope I answered your question about.
Yeah, I think so. I mean, you're going to get poles that hit each other, right?
Yes.
But that'll give you logarithms generally. Right, dealing with, because I is divergent, you had a counter term, and you get similar. You normally.
Yes, I think in those in the divergence case you have to.
But the final solution will be always away from pole, so it will might end up close to some pole, but not at the pole. So in the end, there's going to be no.
Exactly.
Then there's going to be a finite value of this function that you will compute.
Exactly.
But that's like saying that the epsilon expansion is UV finite. I mean, it's a bit risky, right? Are you doing the epsilon? Are you finite distance away from the pole, or are you an infinitesimal distance away from the pole?
What I will do is to be finite distance away from the pole.
Okay, then you're good. Thanks.
So there is a mathematical package nb.m developed by Michael Cyclone. There are developed algorithms that reduce the number of numerical integrals generated from shifting contour. So for the kind of integrals complicated like this, different approaches of shifting contours might end up with different numerical integrations, so which can be time consuming if you don't do it wisely. But there's actually there are amazing algorithms that you can reduce the number of numerical integrals generated from here. And also the numerical integration, on the other hand, you can use the Cuba. It's a famous numerical integration software. And the new version actually supports Mathematica now. You can just call it directly from Mathematica. There are 4 different methods you can choose just to compare and to double check your results. That's indeed what we did. So there's another one for the stress tensors, another equation for the stress tensors. In this case, actually, because of some trick which I will mention later, this guy can be calculated analytically. The stress tensor is looking like this, and you heat it by a derivative, and you get some delta functions here, right? So because of these delta functions, you can actually freely integrate out one coordinate, and in the end, after that, basically you can use the 3-leg star triangles, and you in the end you end up with an analytical expression. So let's, for simplicity, just consider this T and phi tilde. Later, if you want to attach the external legs, it's quite easy. So you heat it by a derivative. You basically want to evaluate this integral for the moment. So you heat it by derivative, it becomes some delta function between x1 and x5. You integrate out x5, it becomes just this kind of diagram. And you remove 3 legs, 3-leg stars, 3-leg stars, and then you got this. So that's how you can get the analytic expression, but it's not that easy. So first of all, this partial T is a conformal primary null state. So the result you are getting would be proportional to this expression, which is odd under x2 and x3 flip. But when you do this odd identities, you have the piece that is even under x2, x3 flip. So in the end, what you are getting is 0. So that's not too surprising because of the conservation, right? I mean, we are trying to calculate the left-hand side, but if you hit it also on the right-hand side, this is because the conservation basically tells you this guy should vanish at generic x1, x2, and x3. So so a trick was introduced by Fredkin and friends here. So you basically shift your dimension a little bit. If I introduce phi a and phi b, and in the end you take the limit of delta A goes to delta B, and because this piece actually is proportional to delta A minus delta B, so that cancels the vanishing piece of the left-hand side. So in the end you get some finite piece of information. So you attach the external propagators, you get indeed an analytic expression. So I think this actually makes it very clear. They are meromorphic functions, right? They are with It's gamma functions, and this psi is basically the diagonal function, and they just have some poles. There's no other kind of singularities essentially. So now you can do it. So what we did is basically try to solve it at finite couplings. So for the orange one is the one that comes from the propagator renormalization. The blue one comes from the one that comes from this long expression, this guy, because we don't know it analytically, we have to do the numerical calculations, and that's what you are getting here, essentially, a few dots. And the solution at d equals 7 is that at this value, so you indeed find a solution at this finite coupling case. But also notice that this bootstrap equation has no solution at d equals 5. This is because of unitarity. And remember, I said that Polyakov's relation was based on unitarity conditions, so it's essential. So in this sense, you don't have any d equals 5 solutions. Yeah, so that's the case for lambda phi cube.
So what's the lesson here, that you're saying that you provide evidence for the existence of this fixed point in 7 dimensions?
Yeah, maybe, but okay, I think let me say it in this way. I think we shouldn't trust this, because in d equals 7 there's no this CFT is probably complex, right? Because of the instability issues and everything. So so I'm going to move on and actually do the calculation for ON.
So what happens if you do phi cube theory in 6 dimension? Is there some fixed point in the epsilon expansion?
Yes, there is fixed point in 6 plus epsilon and 6 minus epsilon.
No, 6 minus epsilon is well known. It's just Li Yang. What happens for 6 plus epsilon?
For 6 plus epsilon is because I think you should consider solitons, and after consider that, you will see that your scaling dimensions actually have a small imaginary part, so it's not fully elementary.
But does this 2.53 comes more or less right in the epsilon expansion? I mean, I'm just saying.
There's no correct way to. I don't think there's a concrete way to do epsilon expansion. You can use a bootstrap, actually. You can use Gliozzi's method of bootstrap. And in fact, that's also roughly here, I think. So that's the only piece of information you can compare with.
There's no way to the epsilon expansion because, of course, the fixed point is for 6 minus epsilon, not for 6 plus epsilon.
Yeah, it's not renormalizable in some sense.
Well, just the beta function is the wrong sign.
Yes. And you get g to be some t squared to be some negative value, I think. Yeah.
So can I just ask, these two equations you have for delta, they're only different because they have slightly different truncations embedded in them, is that right?
Sorry?
Well, I mean, the equations, for the full theory, there should be some single equation involving delta and d. So you have two different equations, but that's because you truncated them somewhat differently. Is that right?
No, the actual 4 equations should be including here the higher diagrams, like g to the 4th and the second loop. And all these
but as you add more terms, the equation should become the same. Is that right?
No, they shouldn't become the same, because we are trying to solve 2 variables. One variable is delta, another variable is g squared, essentially. You need 2 equations. And these 2 equations come from 2 different places. One is from this diagram. This is the renormalization of the vertices. And another from the renormalization of the stress tensor 3-point function, essentially. So they are different.
What do you get for g squared?
I didn't record it here. Actually, I did. I have to scale it back to. Okay, this is g squared, but I have to scale it back to the Euro OPs, which I didn't do. Sorry about that.
But it's a factor, what, 10 to the 8?
Yeah, but that's because of my normalization. I'm normalizing it like this, phi tutor, like this. So basically, or in other words, my 3-point function looks a bit weird. So,
yeah.
But is there some sense in which this solution becomes weakly coupled when you send dimension close to 6?
Precisely what I'm going to talk about next. So so this is right after dimensional regularization was invented. Actually, Mark came up with the first solution of this bootstrap equations. So I should mention there are two ways, two diagrams, right? We considered the vertex diagram has a pole at d/3, while also the propagator diagrams, the stress tensor diagrams, has a pole at d-2/2. So these two poles do not coincide at the physical spacetime dimension, but they coincide at d=6. So in fact, you can do this kind of calculation by setting d=6 plus epsilon, and by setting delta equal to d-2/2 plus some alpha numbers. And these two diagrams, the i's and x, become something like this. And you set them equal to each other, you solve for alpha, and this indeed agrees with perturbative calculations, essentially. So in fact, you go back to the space-time dimension. In some sense, what I'm stressing, what I'm saying here is this. So the usual perturbative calculations are at the point where these poles coincide, essentially. So you can do it for O(n), and the trick is not too heavy. The trick is just to introduce another field which we call F, which is F equal to phi square from the Hubbard Snow-Rich transformation, essentially. So in this case, you have three equations. One is for this one pi vertex of these three fields, another for the propagator of phi's, a third one for the propagator of this F's. So these two you can solve analytically in the usual sense. This one you have to do it numerically. And again, it's actually a little more complicated because now you have two dimensions. You have to the analytical continuation is a little bit more difficult. But anyway, the md.m package deal with this correctly. So in the end, you get this. So why I'm plotting it in this way, this is a bootstrap equation. This is the one coming from the vertex. This is the one coming from the propagator for phi's. This is the one coming from the propagator for F. And because there is a phi loop here, there is a factor of n apparent here. And what I'm plotting here is in the delta phi and delta F plane. The yellow one is chi1, the one for phi's, and this blue one is the one for F, and this green one is the I function. And for them to have solution, they have to be equal to each other, essentially. So the joint point is at this point. So as you can see, it's not too precise. For example, if you set n equal to 1 for the Ising case, the phi's are good. They are roughly speaking at the same value. But on the other hand, delta F is quite far away. It gets better when you go to the Largen limit, but in Largen limit, perturbative calculation actually works. So you shouldn't be too surprised that it goes back to the actual value. I hope this improves. I hope this improves as you go include higher diagrams. In fact, that's one of the main motivations that I'm doing this kind of research. I'm more curious about whether these crossing equations, these bootstrap equation gives you a convergent answer or not in the end. Okay, and similarly, you can go back to the Largen calculations. you set delta phi equal to 1/2 plus some 1 over n corrections, that f equal to 2 minus some 1 over corrections. Your functions become something like this, and you can solve for the C1 and C2. In fact, I mean, the large result about the unworked model we all cite as bootstrappers actually was calculated in this way. Yeah. So, so I was using Mailing barns as one way to do analytical continuation, but there are another very interesting and popular technique called sector decomposition. I will be very brief because basically these gamma functions, they have integral expression in terms of this. You can actually evaluate them. You see that indeed it's convergent at z equal to 1/2, but it's not convergent when you set z equal to -1/2. But this is only because you didn't do the analytical continuation correctly. So what you should do is actually to do this. I mean, to break it into 3 pieces. One piece is the integration from 1 to infinity, which is finite, and you can just use it normally. Another piece is this integration from 0 to 1, but you in the first integral you just subtract the part that causing you trouble, gives you infinity, and then add it back. But this guy can be evaluated; it gives you a pole, and this guy can be just used numerically. And you can see indeed now this new expression works as you go, as you move away from the poles. So this is how they do analytical continuation for the Feynman diagrams. And in fact, there's another tech. The name sector decomposition actually comes from this. So if you have the integrals with more than one integration variables, it's not so easy to read out that which piece is causing you the singularities. So so you have to what you are going to do basically the singularity comes from the region where x and y both vanish simultaneously. So they call this overlapping of singularities. So basically what you are doing is to slice your integration region into 2 pieces. Okay. One piece is this triangle, another is the bottom triangle, but you add the substitution, you set y equal to xt in the first sector, you set x equal to yt in the second sector, and then you basically bring it back to an integral in this square. And for this kind of integrals, it's much easier to read out what is the proper what is the piece that causes you singularities. So you can do similar things as here. You subtract the piece that causes you singularities, and then you add it back. You have some poles here. So this kind of analysis is called sector decomposition, and is quite popularly used in calculations essentially. So these are some details about sector decomposition, which I think I will skip for the moment. Why are we talking about sector decompositions? Is because it's also straightforward to use them in our kind of integrals. So the integrals we are dealing with are basically this kind of integrals. These are just like x1, 2 to the power squared, x1, 3 squared, all these propagators with certain powers, and you can use the Gaussian representations. You use this formula and you bring back to Gaussian representations and perform the Gaussian integral. You get this representation called Schrödinger representation of the Feynman integrals. And these u's and f's are just polynomials. I think we all learned this in our schools, in our QFT courses. There's another representation called Feynman representation, which, interestingly, very recently, there's another one called the Lee-Pomorowski representation, which is the one that kind of is most direct when you do secretary decomposition. So it basically looks like some polynomials, and with some powers, the integration over this. So well, anyway, you can just follow the standard steps and to derive the corresponding U and F polynomials, and it will give you directly what the polynomials looks like. So then you can just do sector decomposition to evaluate these integrals. So, but well, anyway, for us, for the first loop, we just use main invariance. But as I'm explaining here, in principle, you can use sector decomposition to deal with a similar problem, to do the analytic continuation. So let's compare these two methods. The main invariance representation is you need to integrate of gamma functions along the imaginary axis. If you look at this expression, this is large behavior, large B behavior. There's a decay piece, but there's also an oscillating piece. Because of this oscillating piece, I mean, it's not very easy to do the numerical evaluation of the integrals. It's oscillating, it's not too smooth. You have to sample properly. There have to have enough points to be able to sample this oscillating. But on the other hand, the Feynman or Lee Pomorowski representation has smooth integrand, which makes the numerical integration easy. So they have developed methods to do this, so-called quasi-Monte Carlo simulations. So in some sense, what I'm trying to say here is that this representation is very smooth, so it could be better for numerical evaluation for later. So the workflow is that you find a proper representation of the conformal integrals, you analytically continue it using either main invariance or sector decomposition, and then you numerically evaluate the integrals. So let's talk a little bit about the future. It will be highly desirable to push it to higher orders to check whether it gives you a better answer or not. But at face value, this is very complicated. It's a 12-loop integration. 6 of them can be integrated using star triangular formula. So, but on the other hand, we actually derive the main invariance representation, and we realize that you have 16 integration variables. This is a bit crazy, in fact. But on the other hand, you can use Feynman or Lee Pomorowski representation. It contains less integrals. However, we talked to a friend, and he did some rough estimation about how many sectors do we have. So we have 10 to the 6, roughly, very rough estimation. And in the work in 2015, the syntactic collaboration was dealing with this kind of diagrams. And what they are dealing with was like 20,000, about 20,000 sectors. It took them 1.5 hours to do this calculation. So I'm including this just to give you a feeling about how difficult the second it is to include the higher loops. I think we should still be hopeful, be optimistic. In 2008, when the first Bootstrap paper came out, nobody would have imagined what kind of calculation we can do nowadays, right? So, yeah. So I think a very important philosophical question is whether this root recurrence is convergent or not. So there was a famous argument by Friedman and Dyson about the divergence of the perturbative series of QED. He was basically saying that when the coupling of the QED is negative, the vacuum would be unstable against creating more and more particles, and so it should be divergent. Actually, this can be made concretely for quantum mechanics systems. If you consider the potential of this form, okay, with x squared and some lambda, and you consider the ground state energy of this system, And you do perturbation series calculation, you get a ground state energy in terms of this perturbation, and you actually realize that this perturbation series is divergent. That's essentially because at negative lambda, this physical quantity has a branch cut, and there's a small imaginary piece which comes from the decaying of the ground state, essentially. So we are doing perturbation around the branch point so that the radius of convergence should be 0, right? So the series is asymptotic. However, these bootstrap equations kind of are working in the finite coupling region, where you are away from the branch point, and therefore I should see probably there's some chance it gives us a convergent answer in the end. So that's actually the most important motivation that I'm working on it. Also, I think the same thing, I should say the same thing happens for quantum field theory. In the early papers, there is an explicit proof, which sounds surprising, but yes, there is an explicit proof for the divergence. And the divergence is partially due to the rapid growth of the number of Feynman diverms at each loop. There are some other reasons, but since these bootstrap equations have skeleton expansions, so you have much less diagrams at each loop. So there's a chance that it can be convergent. So essentially the question I'm bringing up here is this. So suppose we include at higher and higher loops, we get a number. We include first loop, we get a number. We can include second loop, we get a number. And a third loop, we get another number. Would this series converge to the physical value? I hope I don't have any direct ways of answering this question except for doing the calculation and see how the answer we are getting. So I hope with further technological developments, maybe we can approach this problem further. Yeah, so there are some other modern things we might be able to use. Especially the one thing is so-called dimensional recursion relations. So there are relations that between these general Feynman integrals at different space-time, but the powers of the propagator would be shifted. So the hope, of course, is that could we use these relations to bring the integrals into the region where it's convergent? Right, it's not convergent in 3D, but maybe after using these recursion relations, you go to 4D, 5D, but in that case, you can numerically evaluate directly because it's convergent. I'm not sure, and we still need to think about this. And another further question is how to deal with gauge theory. I think people didn't think much about how to deal with gauge theory in the early days. But as I mentioned, that the Largent readout for the Owen vector model and the Largent readout actually for the Grosvenor models was calculated using this bootstrap approach. But if we can come up with something that works for gauge theory, can we like improve the Largent calculation for gauge theory? That's something we need to think about. And that's my talk, and thank you for your attention.
Thanks so much. Any questions?
Can I ask a question?
Sure.
You can. It's a very basic question. I didn't understand if there are first principles on your very basic master equation you start with. Where does it come from? It's something I didn't get. Can you develop a bit on the derivation of that formula?
The derivation of this formula.
Right. So, for instance, yes, this one.
I think for me, the most direct way to do this is to actually consider the renormalization of your couplings. You start from the Lamp-Phi cube theory. you write, you do the renomination in the Euro sense. In the Euro quantum field theory, how would you do that? You just write down all the Feynman diagrams at each loop. There's a concrete way to write down these diagrams. And I think after that, what you need to do is just to regroup them. For example, if you see some diagrams of this form, right, you just call it a renormalization of the vertex again. So you just reduce it back to a skeleton expansion instead. And that's how you will get it. You will get this, I think.
So aren't these the same as truncated Schwinger-Dyson equations?
Yes, it's Schwinger-Dyson equations, essentially.
No, but I don't think you will get this equation. What you will get is some other equation, which will look rather similar, but it will have vertices not yet conformal, because since we are just doing what you're proposing, let's just do phi cube theory. Let's just study it from the UV to IR. So we will get some equation which will have this form because you grouped diagrams, but the vertices are going to now have both UV piece, which is not yet conformal, and IR piece, which is conformal.
Right.
So now you have to do another step in the argument, which is to prove that somehow UV piece does not contribute or is subleading, or so we can forget about the UV piece.
And that piece is not clear, I think.
I think these other people that you cited, these people from St. Petersburg, Vasilyev and others, I think they have some comments about that in some of their papers.
Okay. Yeah, I kind of missed that.
Wait, why is the IR piece conformal? Are we close to are we doing 6 plus epsilon expansion? Yeah, for phi cube theory.
Yeah, you are just trying to, you're assuming kind of from the start that you're doing some theory which flows in the IR to a CFT and starts in the UV as phi cube. And you're saying, let me just compute this phi cube 3-point function in the IR.
Yeah, in some sense, I think phi cube is not really a good example, right? I mean, phi cube is in the UV, so I think we should talk about ON.
Exactly, yeah. So phi cube is also in the UV, so okay, you have to like invert the logic.
Yes, but let's talk about ON. ON is concrete. I think ON indeed is in the IR.
So aren't you at the fixed point where everything is conformal? It's not.
Sorry, I didn't get to the question. Sorry.
I mean, aren't your equations valid strictly at the conformal fixed point?
Yes. These are the equations that is valid. I mean, strictly at the fixed point.
In which case, the distinction between IR and UV doesn't make much relevance, does it?
Yes, correct. I think that's probably why it still works for non-phi cube.
Hugh, but then you cannot derive this equation.
Yeah.
The way to derive this equation is to throw in also UV.
Yeah.
Then you can do perturbation theory, but then in the end you have to pass to the long distance limit. And somehow you should be able to find that what you have in the UV doesn't matter.
Well, yeah, you take the Schwinger-Dyson equations.
Yeah, you take some sort of Schwinger-Dyson equations, which will involve full vertices, and you should have to show that somehow the short distance part of the vertices drops out.
Well, normally in Schwinger-Dyson, there's a bare coupling, which you can kind of drop in these equations.
No, you drop because the bare coupling, it scales differently from, when you go to long distances, it scales differently from this some of the diagrams. So after rescaling, it will go.
Well, another way of saying it is that you're looking at the Schwinger-Dyson equations in the long distance limit.
Yeah, I think that's.
Yeah, right. That's more direct.
I had another question. So you mentioned that here there are fewer diagrams, but do you know how many diagrams are there in each order? Like anything is known about the growth of the number of diagrams?
I personally don't know, but I would imagine it's probably known, right? I don't know any references.
Well, it's the number of primitive Feynman graphs which appear at
Yes.
each order. I'm not sure whether there's any.
That grows factorially. Yeah, but after for skeleton expansion, I don't know actually. It's probably something to work on.
So for your hope, what you would need is that okay, the number of graphs is not too large, and that the individual values of the graphs are also not too large.
Exactly, but the second step, the second piece of information is really hard, right? I mean, how would you estimate a lot of gammas, a lot of integrals? I think in the phi cube calculation, they have some okay. In the actual phi cube proof, they have some lower bound about the Feynman integrals that contribute at each order. And also, I think another important piece is that these perturbative series are not alternating, so they are always positive, the coefficients. So, and also there's factorial growth about this factorial growth about the number of diagrams. So I think all three pieces of information helps you prove that indeed it's divergent.
And the general hope here is that this would be somehow more controlled than the epsilon expansion.
I hope so. I mean, to be honest, the Borel resummation procedure always looks to me a little bit arbitrary. Well, it's concrete, but well, I think probably we can view this as a way to resum the perturbative series, or maybe we can view this as I said, maybe it gives us an actual answer, actual convergent answer. But this is probably too philosophical.
Sorry, can you try to match with the Largen limit? No, in the Largen limit, the series becomes convergent effectively. So you throw away many diagrams. The factorial growth is tamed to an exponential one. So you are hoping here that something similar happens at the end. No, you shouldn't have a factorial growth, otherwise you won't be convergent. Is there a way in which you can match Largen with your result in some way?
No, indeed. I mean, if you there is Largen, so these diagrams, their behavior at Largen are clear. So for example, this diagram, vertex diagram, at Largen it becomes something that scales at n to the third, and also for the rest of them. Requiring them to solve the Bootstrap equation, you indeed figure out what the Largen really is. So I think this perturbative, going back to the derivation of these Bootstrap equations, I think we are seeing the more formidable perturbative result. This is kind of encouraging that these equations are probably correct. Right, so.
Are there any further questions? Okay, if not, we can thank Junchen again, and thanks everybody for joining us. As I said, we will try to have a seminar every Wednesday. The announcement will be both on the Slack channel and on the Research Seminars website. We do not have anything scheduled for next Wednesday, but there may well be something that comes up, so stay tuned. And then the following several Wednesdays are all booked. Thank you.
Thank you very much.
Thanks, Jung.
Mm-hmm.